in backward differential formula, the method is said to be what? A stable for K1 and K2. From K3 down to K6 is A alpha. And from K7, it becomes unstable. However, this method is very, very important, because it's usually used to solve STEAM ODE. And most of the code you have embedded inside MATLAB often use backward differentiation formula. Before we proceed, we have limitation for linear multi-step method in equation 7. It says that no explicit linear multi-step method in 7 is astable. Then the one that is astable is not greater than 2. Example of such is the trapezoidal rule, which is given in equation 10, which is of order 2, and the error constant is what? -1/12, depending on the angle in which we use to get the error constant. Some can be 1/12, while others can be -1/12. Then the proof is documented in Aaron et al. 1993. The limitation of linear multi-step method allowed Cash 1980 to develop an extended backward differential formula, which is given in equation 11, and the method is astable up to order 4 and become A alpha stable for order 5 down to order 9. The plots below show for EBDF in B, while the BDF is shown in A. We also have block method. Which is the composition of linear multi-step method in 7, meaning that you must have minimum of 2 linear multi-step methods coming together to form a block. You can have 3, you can have 4, you can have 5 to form a single integrator, which has capability of yielding block of solution at every cycle of integration of interest. We all know that block method was first introduced by Miller, and we have many authors that have worked on block method. But our emphasis is on Chu and Hamilton. Which developed multi-block initial value method as a form of predator corrector, and is given in equation 12, where the coefficients AJ and BJ and the solution value Yn plus J and the function solution Fn plus J is given in equation 13. We know that from equation 12, when we set S equals to 1, it will give us the conventional linear multi-step method back. It will give us the conventional linear multi-step method. Also, Chantier in 1993 further clarified the inadequacy of Chu and Hamilton on explicit and implicit method. That is to say, Chantier informed in his article that the Chu and Hamilton work is not implicit in nature, that it is explicit in nature. Then we also have many people that have worked on that initial value multi-block method. We also have them. So we have another type of method which is different from the conventional initial value method that we all know. And this is what we call boundary value method. How does it work? Although boundary value method was initiated by Bugano and Trigate in 1998 in its monogram, we also have some work in it 2002, 2009, and 2012. This new approach is given in equation 14, where the A contain Y0 to Yk minus 1 are the solution input that is required. The B are Yn minus K plus 1 to Yn are the solution input from the final part that is required before we can implement equation 14. As stated here, they told us that the K1 and extra initial solution value in 14, and the formula for it is given in 15. For the final one is given in 16. One of the advantages of boundary value method is that when you are developing this method, you develop the initial and the final concurrently with the main method. The three moves together simultaneously. Unlike in initial value method, when you develop a method, you have to, after developing the method, you have to look for the method you use to implement it, the predator you use to implement it. But in boundary value method, you develop the three concurrently. As you are developing the method, you are developing the initial and the final concurrently. By this, the method in 14, which is assumed to be what? K1, K2 stable, is used with what? K1, K2 boundary condition. We need to know that that K1, K2 that we are talking about, the K1 is telling us the number of roots inside the unit circle. The K2 is telling us the number of roots outside the unit circle. When we take the stability of the polynomial, we must have done the stability polynomial before we can be talking about the K1, K2. When we find the stability polynomial of the method, it will give us some roots inside and some roots outside. Those roots inside and those roots outside will tell us how to couple the initial and the final together before implementation. Then we have some boundary value method in the literature. We have some, I only mentioned a few here. We have the generalized backward differentiation formula. We have the generalized add-ons method. We have extended trapezoidal rule. We have top order method. We also have for the case of second derivative, but my emphasis is just on the first derivative. We have for the case of second derivative, generalized extended second derivative. We have for the case of the modified generalized method. So here we have formulation of multi-block boundary value method, which is the topic for today. When you say multi-block boundary value method, we are starting with the conventional initial multi-block method of Chu and Hamilton and Ekile and Muka 2015. The method is given in equation 17, where there are coefficients, the block solution value, and function value is as well given in the equation 18. Here, Yn plus J are multi-block of non-overlapping solution value. In this work, we are working with non-overlapping solution value. We observe when we try to find method with overlapping solution value, we observe that in their stability, the stability plot is cutting each other, and it will be difficult when you are dealing with stiff problem. So we now strictly focus on non-overlapping solution values, and where the functions are as well to are non-overlapping solution function values, as given in 17. Here, the block shift operator E is defined as E raised to power Jyn, which is given as what? Yn plus J. Also, we have the first and the second characteristics matrix polynomial of 17, which is given in equation 19. Then the stability, when we find the stability polynomial for the multi-block initial value method, we have it in equation 20. Then the stability for the method as a whole, when you apply it on a scalar test equation or Danguest test equation, when you apply it on it, you have equation 22. You have equation 22, where some conditions are given below, where the Z equals to what? Lambda H. And the real of Z must be less than 0. How do we now implement multi-block initial value method as a multi-block boundary value method? Now, we try to derive our multi-block boundary value method from the Chu and Hamilton using the method in equation 23. Here we have blocks. We have multi-blocks of solution inputs from Y0 down to YK1 minus 1. Then we have Yn minus K2 plus 1 to Yn, which are the final multi-block of method that we must couple along with the method in 23 before we can be talking of multi-block boundary value method. The coefficient AJB, AJ are also determined by imposing our H2SK plus 1 truncation error. One of the advantages of this method is that it has a maximum order of 2SK, where the S is the dimension of the block and K is the step number of the block. This is no doubt is an order advantage of multi-block boundary value method over conventional boundary value method. In boundary value method, the order is what? The order is 2K. In boundary value method, the order is 2K. While in the case of multi-block boundary value method, the order is what? 2S plus K. That S can be 2 from 2, where S is greater or equal to 2. It can be 2, it can be 3, it can be 4, it can be 5. Now, we need to talk of how the distribution, how are we going to implement this multi-block boundary value method. We have for the case of K1, which equals to what? S multiplied by K1. The K1 here is the number of roots inside the unit circle. But since we are dealing with multi-block boundary value method, the K1, which equals to S dot K1, is the number of roots lying inside the unit circle. Then we have K2, which is S times K2, which is the number of root lying outside the unit circle. Take note, we must have taken the stability polynomial of that method. It's after we take that stability polynomial of the method before we can be talking of Q1 and Q2 of the main method. Also, we can generalize that main method. We can make it in a compact form or in a matrix form given in equation 24, where the A and B are two-place matrices. They are block of two-place matrices. The A and B, you observe from the equation 24 on our right-hand side, the summation J0 to J equals to 0 to K1 minus 1 and A naught are the initial solution that we need to bring in. Then if you move down, AK, that AK yn plus capital N minus K2 plus 1, down to the summation J equals 1 to K2 are the final solution we need to bring in. It's showing us the distribution. Why the inside from that 0, where we have that capital 0 we have there is a column vector of zeros. Where we have it, it's telling us that the method has not been shifted. The method has not been shifted. That's why we are having that 0 zeros there. Where Y and F are the multi-block of solution and function vector of 24. The A and B, as earlier mentioned, they are multi-block two-player matrix obtained from the main method without initial multi-block formula and final formula. For the A, we have the A. You see it, we have the A. From the first column, A naught to AK1 are the initial solution. The initial solution we need to bring in. Then the last row, the last column, we have AK down to AK1 plus 1. Those are the final condition we need to bring along to couple both the initial, the main, and the final together. As earlier mentioned. So the next stage is to talk about the locations of zeros of a polynomial. Here we tell us how the root distribution is being gotten. How we got our root distribution, we want to talk it here. Firstly, the characteristic polynomial we seek is root distribution is given from equation 20 and 22. That is to say, suppose we have a matrix polynomial given in equation 27. We take the determinant of that matrix polynomial in equation 27. When we take the determinant, we have what is in equation 28. We have what is in equation 28. In equation 28, that Q represents the dimension multiplied by the K step number of the block, which is Q equals to what? S is the degree of the polynomial and K is the degree of the matrix polynomial. Now, we want to assume that we have D1, the roots inside the unit circle. When you have absolute of R less than 1, what we are saying that all the roots are less than 1. We have them. R, absolute of R equals to 1. We have roots on the boundary. Then when R, we have roots outside the boundary. So we need this condition is what will make us to give some definitions. Q1, Q2, Q3 form Q. That is to say, when you add your Q1, Q2, Q3 together, it's going to form that Q. Then we are at liberty to give this following definition. The first one says that the polynomial in 28 is said to be of root distribution type Q1, Q2, Q3 if it has Q1 number of 0 inside D, Q2 number of 0 on D, D2, that D2 is root on top of root on the boundary. While Q3 is number of zeros inside D3, where D3 is telling us about root outside the unit circle. Now, the B part is telling us about Shor matrix polynomial. We all know Shor matrix polynomial is the same thing as we saying astability. It means that all the roots must be inside the unit circle. We don't want any root to be on the boundary or outside. That is to say, Q1 equals to Q, Q2 and Q3 must be 0. Then we have in C, monomial matrix polynomial. Here we are talking about zero stability, whereby we have Q1 on the Q1 inside the root, which are the roots inside the unit circle. All the roots are less than 1. Then we have Q minus Q1. That Q minus Q1 must be simple. That is to say, it must just be only one root. Why? all the roots, why we must not have any root outside the unit circle. For this reason, we now want to generalize the matrix initial value method. The one we mentioned before in definition 1 and 2 are for matrix for initial value method. How are we now going to relate it with matrix for boundary value method? Definition 3. In matrix, in boundary value method, we talk about AK1, K2, 0K1, K2. That is to say, we have some root inside the unit circle, we have some root outside the unit circle. For SK1, SK1, K2, we are talking of short matrix polynomial for boundary value method here. The roots, we have the roots must satisfy the condition in 31. Must satisfy the condition in 31. If you watch that condition in 31, you observe that there is no root. There is no root on the boundary. No root is containing 1. No root is containing 1. It shows that it's giving us the attribute of astability, which says that all roots must be inside the unit circle. No root must be on the boundary. That's what the SK1, K2 is telling us. But for the case of boundary value method, all the roots will be shared into 2. Some root will be inside, some root will be outside. No root must be on the boundary for it to be what? SK1, K2. Then for NK1, K2, we have some root on inside the unit circle, we have some outside the unit circle, and we have 1 on top of the boundary. We have 1 on top of the boundary, which is given in equation 32 as well. Then we have the following definition. We all know what is astable or what is zero stable. In boundary value method, we don't say astable, we don't say zero stable. All what we say is 0K1, K2 stable and AK1, K2 stable. In definition 5a, 0K1, K2 stable, we say that a method, that multi-block boundary value method is 0K1, K2 stable if the corresponding first characteristics matrix polynomial in 19 is what? NK1, K2. You know, as earlier mentioned, NK1, K2 is polynomial, which is the same thing as normal zero stable in initial value method. Then we have for K1, K2 is absolutely stable for a given Z in a complex if the corresponding matrix polynomial in 21 is what? SK1, K2 matrix polynomial. Then we also have some definition in C and D as well that satisfy multi-block boundary value method. Now, we want to talk about the Wiener-Hopf factorization of a matrix polynomial. Because here we show us how the root distribution is being formed. Is it true that when we have a matrix, we can find the determinant of a matrix and get some root inside the unit circle and get some root outside the unit circle? The answer will be gotten from this Wiener-Hopf factorization. To obtain a Wiener-Hopf factorization of matrix polynomial, we seek the root distribution of a determinant of a polynomial in factorization form, which is given in 33. We have a matrix. Our mission is that when we have a matrix, we want to look for a matrix whereby when we split the matrix into 2, the determinant of each of them will give us, one of the matrices will give us all the roots inside a unit circle, and the another matrix will give us all the roots inside or outside the unit circle, as documented in equation 33, related to the interior and exterior of the unit circle, where our F and U is given, such that the roots satisfy the condition that when we take the determinant of R minus K1 F of R, we are expected to have all the roots outside the unit circle. And when we take the determinant of U, we are expected to have all the roots inside the unit circle. Because of want of time, there are many conditions that are attached to this Wiener-Hopf, which I could not bring in. But there's a theorem which is given in theorem 6. This theorem showcases how that root distribution, the process, how the root distribution is being done. The theorem is given in Gombe and Kern in 1960, with the proof also in the textbook Gombe and Kern in 1960, where we have our roots, the one for outside and the one for inside, respectively, for G-1 and G2. Then we also have the factorization is said to be canonical if all the partial indices are 0. If all the indices are 0, if you go back to equation 37, 38, equation 37, 38, we have it after splitting the matrix into two. We have that equation 39, where the diagonal contain rg1 to what? R raised to power g1 to r raised to power gs. That g1, the indices, that partial indices, they must all be zero before we can have canonical. What the partial index is telling us that it's telling us how the matrix is. It tells us how the matrix have imbalances or the twisted of solution around the origin. But in our case, when G1, G2 are zero, you observe that the roots are in the origin. The roots are all in the origin. That's what that equation 39 is trying to explain. Then the remark here tells us about the correct implementation of the multi-block boundary value method. How does it work? The condition for multi-block boundary value method is that when you take the stability of the first characteristics polynomial in equation 20, you take the stability of the method as a whole, they must all have the same root distribution. In the course of this work, we derive some method whereby the root distribution of the first characteristics is different from the root distribution of the whole method. So when we get that type of method, it is very difficult for us to implement. So we have to emphasize that the root distribution of the first characteristics polynomial, when you take the determinant, must be equal to the root distribution when you take the stability of the complete method together for all value of z in the stability region, as given in definition 5. Now, we want to talk about the composition of the initial, main, and final method. The continuous problem, the problem we want to solve, the continuous problem will only provide initial condition of why not. Whereas the remaining or the extra initial block of solution need to be provided, and which is given in equation 40 and 41. And when we couple everything together, it becomes a one block method with high dimension. Meaning that we don't need any extra method during the implementation, which we can see in equation 42, and the multi-block of solution and function is as well given in 43. Now, the coefficient matrix of AN, A subscript N, and B subscript N is given in the next slide. The AN, if you watch the left answer inside this matrix, you observe that on top, A11 to A1K1 minus 1 are the initial conditions we need. Then we have the A0 N minus K2 plus 1 down to N are the final condition we need. While the middle is the main method. Which can be shifted to any dimension that we want. As earlier mentioned, the 42 is equivalent to one block method, which is given in 45, and the block solution and function values are also given in 46. We have the A0 and the B0 given. Thus, we are at liberty to state the following definition also. The multi-block boundary value method is in 45 is pre-consistent if this condition is satisfied. That one there is that is a column of 1. It's a column of 1. Then we have definition 8, a minimum multi-block boundary value method. Here, what this definition is trying to say is that if we do not shift the main method, we only couple the main method with the initial and final, then we are talking of a minimum multi-block boundary value method. But if that main method is shifted, maybe you shifted it once, twice, 3 times, 4 times, it's no longer a minimum multi-block boundary value method. And one of the advantages of shifting the main method is that it gives high accuracy during implementation. It gives a very high accuracy during implementation. We have the A bar, which is given, and the B bar, which is given here. And for further clarity, if you go to Bugana and Tigante, the monogram of Bugana and Tigante in 2000, he explained the procedure of shifting, The procedure is documented in that article. Then we have implementation procedure. According to Ivanova and Mazia, 1999, we have two ways of implementing multi-block boundary value method on OD and DAE. The first one, the use of method in 45, which is inversely proportional to the step size. You see, when I was talking about shifting, when I was talking about shifting, one of the advantages of multi-block boundary value method is that you can shift your method to the exact point of the step size each, whereby the iteration will only run once. It will only run once. While the second option here, the use of relatively small dimension of n in 45, here it's like a block by block implementation, whereby it will take the dimension of your work along the dimension of your work, which will be used to divide the step size before you reach the final point. That's what the step 2 is telling us. And we use option 2, although even option 1, 2 was also considered in the numerical experiment. Why? For us to resolve the implicitness in 45, we consider interruption given in equation 52, where the partial f and partial y is also as well given in equation 53. Now, I want to mention some families of multi-block boundary value method. All what I've been doing since are just the theoretical framework of the multi-block boundary value method. So we want to showcase two of the family. We have the first one, multi-block generalized backward differential formula, and we have the second one, multi-block generalized advanced method. How do we formulate this method? So for the first one, we have the formula given in equation 54, where the A and B are expected to be derived. Here, if you go to the left-hand side of the formula, where we have HBIF of yn plus I, you observe that the conventional backward differential formula, where we have I is k, and we try to plot the method, and we observe that the method is only stable for one block 2 points, and it's A alpha, which is 63 degree stable for 2 points, 2 block 2 points. While from the case of 3.2 block become unstable. We even did for four block 2 points, they are unstable. Now, we are at liberty to choose our high, but the I must not be equal to what? K. The high must not be equal to K. And the formula for choosing the I is given in equation 55, where we say I equals to U, and we have U equals to what? K plus 2m all over 2. For the case of even, for the case of odd, we have K plus 1 plus 2m divided by 2. Thus, the method will now be implemented in U, K minus U block boundary condition, where the boundary condition is given in equation 56, and the final one is given in equation 57. However, the B high, the coefficient of the B high, how does the B high, the coefficient look like? We have it. We can set our B high as identity. We can use this as identity, meaning that only the diagonals are 1, while other entries are 0. Or we choose the one given in equation 58, where we have only one on the first column, or we have one on the last column. For the case of when we are solving differential algebraic equation, for the case of us solving differential algebraic equation, the identity is required because we tried to solve it on using the second option, and we found out that singularity was occurring in the Jacobian. So, but the identity own is preferable when solving these. Then we give some illustration. For even for when we split our s equals to 2, we have for 2 dimension, we have 1, 1, 0, 0 for even, we have for the odd, and we have for the any type, we will use A to denote A equals to 3, which is the diagonal. Now we want to fix for K equals to 3 and X equals to 2, where we have our B2 as 1 over 10 of the identity and M equals to 0 in the condition given above. We have the coefficients. The coefficient for the main method is given in equation 60. And it is A21 stable, which can be used with one additional initial condition. Remember that
we are dealing with multi-block method. But the problem of interest comes with why not. Since it is two-dimension, we are expected to have y naught, y1 as our capital Y naught. So we still need to look for what? Y1, and which is given in equation 61. Then couple with one additional initial equation given in equation 62. Then we have the final one given in equation 63. We show the boundary locus of the multi-block boundary value method. We have, for the case of odd number, we have from k equals to 3, 5 down to 15. Then for the case of even number, we have 2 to 14. Although we can go above this, but because of system, because of the processor of our system, so we could not go above k equals to 15. Then we also have for the other variations, when we have s equals to 3, that's dimension 3, we have the plot for k equals to 2 down to 10. We have k equals to 3, 9, 5, and 7. Then we also have when we fix the k and we start increasing the dimension. We increase the dimension 2, 4, 6, 3, 5, 7, as shown in figure 3a and 3b. Then we have the second method, which is multi-block generalized Adam method. We introduce a multi-block method having the form. If you watch in initial value method, the first characteristics always have k. It's either you have ak r raised to power k plus ak minus 1 r raised to power k minus 1 for the case of Adam's types. But here, in multi-block generalized Adam, we assume that our u is not equal to k. We assume that our u is not equal to k. But for the case of u equals to k, it will give us initial value method. It will give us now multi-block initial value Adams method, which is given below in 66. It's given below in 66. And this type of method, when you plot it, they are zero stable, which are only suitable for what? Non-Steve ODE. Non-Steve ODE. So we are at liberty again to choose our u not equal to k, so that we can have a good stability properties. So we want to, the formula for u is given below in equation 67. How do we choose our u? We choose our u by picking k plus 1 plus 2t all over 2 for case of even, and we put a condition for t. Then we have k plus 2t all over 2 for odd, where the condition is as well given for t. According to this condition in 67, then that multi-block initial value Adams method in 66 cannot be converted or cannot be transformed into a multi-block generalized Adam in equation 68, where A and B are block solution inputs that are required before we can implement it. Then the stability plot is given in figure 8. The stability plot for in figure 6, the stability plot in figure 6 are for multi-block initial Adam method. When k equals to 1, k equals to 2, from k equals to 3, we can see k equals to 4, 5, and 6. Then for the case of the multi-block generalized Adam, we have the plot for k 2 to 16, for k from 2 to 16, while when we fix k as 2, and we are now shifting the block size from 2 down to 9, we also show the plot. You observe that the plots are regular. All the plots are all regular. They are all regular. Thus, the method must be implemented with u, k minus u block boundary condition, which is given in the equation 69 and 70. Then, how do we form our AI? Our AI for the case of initial and final is equivalent to what? AU, while AI minus 1 is equivalent to what? A subscript u minus 1. The coefficient of the method are similarly obtained. They are all similarly obtained in the same approach. Then we'll give one example. Example for k equals to 4 is given in equation 71,
where their coefficients are given below. We have the coefficient for A2, A1, B0 down to what? B4. Since it is A2 too stable, it can be implemented with what? One additional initial block, which is given by the coefficient here, and two final additional block, which is given in equation 73 and 74 as well. Why the extra one from the Y0? As I earlier explained, the capital Y0 contain Y0, Y1, but the Y0 inside that braces, the Y0 is given by the problem of interest, but we still require to find Y1, which is given in equation 75. Then application of Wiener-Hopf factorization to obtain a multi-block boundary value method. We want to use the case study of K equals to 4 of multi-block generalized Adam method, where S equals to 2. Here, we fix our Z equals to -1. We can pick any value, but we just want to use -1 so that we can have a precise value, because if you use it with complex number, it will take longer time before the result will come out. So we try to test run it with -1 in 76, give rise to the characteristics matrix polynomial in f of r and u of r, which is given here. This is the procedure. The theory of this is documented in the Gombe and Ken in 1960. But this is the procedure. I've splitted the matrix into two. So we are now going to run the two matrices. We run the two matrices using Newton-Raphson approach according to Butcher and Waza 2013. So when we solve that equation, we have 2,104 options. When you solve it, you have 2,104 options. But out of these 2,104 options, I only pick one option inside, which I showcase in equation 78. This leads to the right-hand canonical factorization among other options. So now this is how to split it. I'm now splitting it. I have my F0, F1 of R, F2 of R square. I have it in the place. This is a mistake, it's R square for the R, the other side is R square, which is identity, the R square, the F2 is identity. So I find the determinant of those method, and I observe that I got all the roots are outside the unit circle. All the roots are outside the unit circle. I move for the case of U hard, which is what? U minus 2, U minus 1 to U naught. After finding the determinants, we observe that all the roots are inside the unit circle, which satisfy the condition for AK1, AK2 boundary condition. So the existence of this gives rise to the band structure block tuples matrix, which is given in A and B, and the result of the 4-block 2-point method, which is given in 82, where the solution function, the solution values and the function values are given in equation 25 above. So we want to talk about the application of multi-block boundary value method on differential algebraic equation. We observe that most of the initial value method, when they implement it on differential algebraic equation, what they do is that they try to linearize the differential algebraic equation back to ordinary differential equation. But in our own case, we don't linearize. We use the differential algebraic equation the way it is given to us, and the procedure is listed below. We have, for example, a multi-block generalized BDF in 54 written in I dimension as given in equation 45. We now apply it on a differential algebraic equation, which is y prime, and we have epsilon of z prime given in equation 83 and 84. When we set the epsilon to 0, it will now reduce the system to 85 and 86. Unlike the conventional way of, unlike authors whereby they try to translate the differential algebraic equation, they convert it back to ODE and solve. We do not convert the way it is. We only assume by taking the first derivative part of the method for the second equation, we set it to 0, while the function still remains. Then we can also use identity
identity, which is given in ing, if the function of the method have identity inside, we can also use the condition in 87, where the initial value are consistent with the condition given in the DAE. The option 86 was considered for multi-block boundary value method, while option 87 was used for second derivative. Option 87 is peculiar with second derivative in numerical experiment. To avoid order reduction when applying multi-block boundary value method on DAE, the coefficient of the derivative part, the coefficient of that derivative part must come from the method of the same order as 85. The method must be of the same method of 85. If not, there will be order reduction. Then we apply some of the method on some problem. We have Bourgain and Tigante in equation 89. So we solve this method with where the maximum relative is given in interval of 0 and 1. The result of multi-block generalized BDF was compared with generalized BDF. We try to compare with the same order. We compare with Jato and Shai 2010. We compare with Adam's method in Amodo and Mazia 1995 to order 6 and 8. Then we go to table 2. In table 2, these are the results for step of 20, step of 40, 80, 160, 320, and 640. If you compare the results, you observe that in terms of accuracy, you observe that the multi-block method for A equals to 2 perform better. They perform better than the compared one. Then also in the case of table 3, we try to bring even A equals to 3 in. You observe that for the case of identity, where our A equals to 3, meaning that we are using identity as diagonal, in that one, you observe that the method perform better than the one that has its column, that has 1 only in the last column. It performed better than it. The identity performed better than the one in the last column. And it was also compared with generalized BDF and also with extended BDF in Ogunfeyitimi and Ikile too. And we also have problem 2. The same thing is applicable to problem 2 too. So in the table, we have here the emphasis of telling us shifting. The shifting comes in place from this place. The case of when S is 120, this 120 is, the 120 we are having here is that we have tried to shift the method. We have tried to shift that method to accommodate it so that we'll run it at 0.1 step size. And we observe that the method perform better than even without shifting. And we compare it with the method of Jato, we compare it with the method of Wu and Sia and the block hybrid SDM. And we observe that the method perform better. For the case of A equals to 2, when we shifted the dimension, perform better than others. Then we also apply it on problem 3, which is taken from Ojati et al. 2006. The results are presented in table 5. To watch it, when we use for case of A equals to 2, we compare with Ojati, Ismail, then secondary BDF and Hero in OD15S. You see that the method has performed the other method of the same order. Then we also now apply it to the problem of index, DAE of index 2 in Bourgain and Tigante, and Ascento and Tigante 2002. That's the method. We apply it directly without converting. We did not convert this problem to OD. We use it the way it was given. And we have the result presented. For the case of multi-block generalized BDF. We compare it along with the one in Bourgain and Tigante. And we observe that as our method begins to grow in step size, it performs better than that. Then we also have for the index of 3, the same thing applicable in index of 3. So the choice of A equals to 2, as noted already in this, is not amendable. When A equals to 2, A equals to 1, we can't use it for index 3. We can't use it for index 3. So we have to use only for identity, where our F part is what? Identity. That's what is applicable in problem 5. And the result is as well given in equation in table 7 as well. Then we have Robertson equation of index 1, 2. We try to compare it with the Robertson equation that is of ODE and DAE. We want to see whether the accuracy will still be the same as if we are dealing with ODE, and we have 6A and 6B. If you check the two, you see that it was just a slight difference between the ODE and DAE. The DAE is problem 6A is the DAE, while problem 6B is the ODE of Robertson equation. And we try to see. We observe that at 10 we have almost the same error constant at time equals to 10. Then the number of in table 9, we listed the number of function called Jacobi, number of LU decomposition, and response time in second at output points of t equals to 0 for problem 1, problem 4, and problem 5. We listed it here. So thank you. These are the references. So thank you.
Very good presentation.
Thank you very much, Dr. Ogunfeyitimi, for your very wonderful presentation. In fact, you have taken us through a treat of extensive analysis of numerical methods for differential equations. And I like to say that I like the approach of your talk. I want to thank you very much for giving us your time. And I want to thank you for taking out time to prepare these very beautiful slides. And for taking us through a very nice treat. So I will now open the floor for questions. Please, if you have questions, you could just use the react button to raise up your hands, and I'll call you. Any question, if you just raise up your hand with the button. Any question?
Hello, sir.
Please use the react button and raise up your. I can't see anybody's hands raised up on the participants list. Anybody trying to ask some questions, please raise up your hands. Okay, good. Dr. Mark, please, can you go on with your question?
Yeah, thank you very much for the presentation. It was quite a wonderful one, though I didn't start from the beginning of the presentation, but I think it makes a whole lot of sense. But I want to actually ask that this multi-block boundary value method and its stability criteria, is it majorly for just first order problem? Does it extend to others greater than 1?
Yes, it's extend. I only use this as a case study. Extend to all other methods.
Now, the thing now is, if you agree with me now that for first order, okay, we can say for certain order of P less than 2, we can say they are astable or thereabout. But for others, for when you talk about higher order blocks for higher differential equation, when you talk about, let's say, second order, third order, fourth order, we don't talk about astability there.
There we talk about Denimore conjecture.
Yes. So in this case now, how do you actually establish the stability, and what do you actually would say about the stability for higher order problems?
Because for higher order problem, the condition, the Denimore conjecture says for the case of the second derivative, if it is for second derivative, the order is no more than 4. Am I right, sir?
You're very correct.
So
the first thing we are going to do is that we are going to first develop a multi-block initial value method. And when we develop it, we check if it obeys the Nemo condition. If it cannot obey it, that's when we want to convert it to what? Multi-block boundary value method. That's when we convert it. So when we are converting it, we will have to be very, very careful that the root distribution of the first characteristics stability polynomial must contain the same root, the root distribution, with the stability of the whole. Because if you watch that condition that the dynamo is trying to say, it's the same thing as what I'm saying, because the dynamo is saying that the method cannot be of order 4. If you go and find out those methods, you observe that their root distribution of first characteristics is not the same as second. Even for normal first derivative, after the BDF for k equals to 7, go and check for k equals to 7, k equals to 3 itself. Check the root distribution of k equals to 3 for BDF. You observe that the root distribution for first characteristics polynomial is different from the whole method. That's when you now be having alpha, you now be having unstable, instability setting. If the root distribution in the first characteristics polynomial is the same as the stability of the whole method, the method will become unstable.
Thank you very much.
Welcome.
Dr. Blessing. Yes, go ahead with your question, please. Oshatuyi.
Thank you, Doc. The lecture was quite insightful, but I want to ask, can you hear me, sir?
I can hear you, sir. I can hear you, ma.
What's the basic difference between multi-block initial value problems and multi-block boundary value methods? Sorry, multi-block initial value methods and multi-block boundary value methods.
Are you saying the difference between the two?
Basic difference between the two.
Thank you so much, ma. You know, when you say initial value method are methods that require only initial condition. I hope you can hear me. But when you talk of boundary value methods, they are methods that require both initial and final conditions. Just like case of initial value problem and boundary value problem. So that's the difference between initial value method and boundary value method. Initial value method deals with require only initial conditions. But in the case of boundary value method, they require both the initial and final. You couple all of them together before implementing. Remember that if you want to implement in your initial value method, you need initial conditions. Your initial conditions must be provided before you can solve initial value problem. So for the case of boundary value problem, if you want to solve it, the initial and the final two must be provided. That's the difference between the two.
Thank you. Any other question from participants? Please raise up your hands and ask your question. Okay, in the absence of no question. Are you trying to ask a question, Dr. Sani? Okay, I think he's not trying to ask a question. Okay. So, in the absence of no question, I want to thank Dr. Ogunfeyitimi for your wonderful lecture today, and I want to say God bless you for what you did today for us.
Thank you, sir.
I want to pray that you continue to progress in your research, and you know, like I put it in the platform that that the person that is going to present is a high flyer in numerical analysis, and I knew what I was talking about, and I thank you for delivering and trying to showcase what you are made of, and I believe that a lot of our participants have learned a lot from today's lectures they have given to us. And I want to say thank you very much for what you did for us today.
Sir.
Yeah. Now, like I said in my last post, I said I was going to create an opportunity for anybody that has any challenge in anything is doing. Maybe you are working on the research and you want us to, maybe you want a guide or you have a problem in your research. And I asked that people, make like slides. People should make slides to present to us. So I was saying that, I asked some students to, if you have any. Blessing, do you want to ask a question? Blessing, do you still have a question you want to ask?
The request, sir.
Do you still have a question? Please ask your question.
Okay, I want to request that can the PowerPoint be presented?
No, the video is recorded. I'm going to paste the video. But don't worry, you get the video, not even the PowerPoint. The lectures itself, you get everything. Don't worry. Okay?
Okay.
Dr. Idowu, do you have questions?
Yes, I have a question, sir.
Okay, please ask your question.
Yes, I have a question for Dr. Seun.
Okay.
So, Dr. Seun, when you were talking about AK1 and AK2,
Yes.
you said something about the roots. You said when the roots are negative, when they are less than 0, they are inside, and when they are outside, when it's greater than, they are outside. Does this method make any account for when the root is complex? You understand what I'm saying? When we have a complex root.
Yes, if the method, I think if you go to the Wiener-Hopf, it's like you not check some of the, if you check those Wiener-Hopf, when I was trying to explain the roots distribution in Wiener-Hopf, you see some complex numbers inside.
Okay, but how do you describe that phenomenon? Because when it is less than, you said it is inside, when it's greater than outside the root. So if it's complex, how do we describe that phenomenon?
So when it's complex.
Yes, when it's complex.
The modulus now,
No, I'm talking of the simulation. You gave us a simulation. You showed the simulation for when it is inside and outside. So how do you describe the simulation when it is complex?
When the root is complex or what?
Yes,
because I need to get
when the roots are complex.
Some of the roots will always be complex. When you have complex number, let me give you an illustration now. 0.00, when you have 0.000 plus 1 I this thing. If you observe those roots now, if you take the absolute of that root, it will be less than what? 1.
It will be less than 1, yeah.
Are you getting me? Those one falls to inside. When you have 1.00000 plus this, when you take the absolute, you observe is greater than 1. So they already fall. It will separate it, it will filter it when you are finding the determinant. The determinant will filter it, we filter the one that is going to less than 1, the one greater than 1, it will filter it for you. Under when you look for the determinant, it will filter it for you and tell you, it will even arrange in ascending order. As you arrange the determinant, it will arrange in ascending order for you to know that these certain roots are for inside, these certain roots are for outside.
Outside. Okay. That simply means it is that simply means the condition there is based on the real part. If the real part is positive or negative.
If the real part is positive or negative.
Yes, this is the real part of the complex number, yes.
Sir, if it is positive or negative, positive and negative together can still be greater than and still be less than. I hope you know, sir.
I know that is when the other part is equals to 0.
Like now, if you have minus 0.0 I, minus 0.0 I is what? That one is less than 1. Am I right, sir?
Yes.
Plus 0.01 plus 0.01 I is still less than 1.
Still less than 1, yeah.
Yes, so if you now have 1 point something I, 2 point something high, plus or minus, it will be greater than 1.
It will be greater
so
than
that's
1.
what I'm trying to say. That it will filter it on its own.
Okay. Thank you, sir. Thank you very much, sir.
Welcome, sir.
All right. Okay, any other question? Oh, okay. So since there are no questions, and none of our students here are prepared to share maybe problems in their research or their problems in their projects or anything. Okay. So I will just give space for some senior professors I have noticed in the participants list to give us like a word from the talk so far. Maybe I'll just call on Professor Odekunle. I don't know if Professor Odekunle is available. Professor Odekunle, are you here with us, sir? Professor Odekunle, are you here with us, sir? Okay. If Professor Odekunle is not here with us, Professor Okunuga, please, could you just give us a word and encourage us as researchers coming up in numerical analysis? I don't know if you are here, sir. Hello, Prof, sir.
Hello.
Yeah,
Are
Prof.
you hearing me now?
Yeah, we can hear you, Prof, sir. We can hear you, sir. Prof, go ahead, sir.
What you have discussed this afternoon. This call for every one of us to know that working together in collaboration is very key. And that is why this platform is set up so that we can share ideas and then don't let the ideas stop here. You move on from there to look at what has been discussed, and then you want to try and connect it to what you are doing in your own specialized area. I think that will go a long way to build up our capacity from this end of the world. I must say that wherever we go, as Nigerians in this field of computational math numerical analysis, all the time we always speak as pliers. And so the same way we must be seen when we are doing this kind of discussion. I can hear the speaker referring to Jato several times. That should show that myself and Jato and some of my students, we wrote some papers together that to say that work is always built up over the years, and we want every one of us to collaborate and build up more work, especially with the younger ones, because by the time the younger ones, you are able to come up with some of the ideas that is being discussed today, I'm sure that you'll be able to go far, far better than what has been in the 90s, in the early 2000s. So we need to open up new areas and keep on opening up new areas. And that is why we need to, like somebody was asking about difference between the initial value problem or initial value method and a boundary value method. We need to go to the basics all the time and make sure that we are very sure we grasp the content of all we need to grasp. Somebody was talking, the last speaker was talking about something about when you have complex roots and some of them are lying outside, or how do you describe the phenomenon? All of this you need to be able to understand. And I can hear the coordinator talking behind that. You take the modulus and blah, blah, blah. So these are some of the things that you need to trash out. You don't expect the lecturer or whoever gives the lecture per day to be able to answer all the questions. It's not on spot to be examined. And therefore, it is to share ideas together each time so that all of us can go back and look at some of the things that have been discussed and move knowledge forward. Thank you, Dr. Ige. Over to you.
Thank you very much, sir. As always, I like to let everybody know that the professor I just finished speaking now was my PhD supervisor, and has always been my backbone, and supporting me all along. Okay, thank you very much, Prof, sir. So any other comments before we call it a day? Any other comments before we call it a day? If you would like us to send you messages directly, since we don't have a, I don't want to, let me just say, I don't want to create any WhatsApp platform for this group. if you want us to send you messages directly to your email, please do me a favor to fill this form. I have put a form on the chat box. Please do me a favor to fill this this form, so that I can harvest your email address to send you messages for our seminar series that comes up every third Wednesdays of every month. And I can assure you that you always have very, very interesting speakers on the line. Now we have Dr. Rufai will be giving us a talk in June. We have Professor Luigi Bugnano will be giving us a talk in July. We have Dr. Fagbade will be giving us a talk in August, and so on like that. So I'll try my best, and if you know if you feel that particular form that is there, you will see that there's a place where we have asked the kind of if you have anybody that you are interested in wanting to speak to us, we'll try to contact the person and you get the talk from that person. Trust me. So I want to thank everybody for coming to today's seminar. And I see a hand up. Dr. Mark, do you have a comment, or is there something you want to say?
Yes, I do have a comment. Yeah, sorry, this is the second time I'm actually talking, and the thing is this: I wouldn't mind to work with if he's disposed to working with me, Dr. Seun, who just finished giving the speech, because if you take note of some of my publications, it has been like third order, fourth order, and all that, and I would want to have a kind of a very close collaboration with him, so that at least we can do something together. If that is disposed to that, please.
Okay. Yes, that's very good. Dr. Seun, please, could you just put your email on the chat box?
Okay.
Yes, just put your email on the chat box. And just to quickly use this opportunity to quickly make a comment. Dr. Mark, trust me, all differential equations, whether they are higher order, right, can still be seen as a first order differential equation, because you can convert them to a system of first order differential equation.
Yeah, I'm aware of the fact, but
once you can convert them to a system of first order differential equation, any method that works for first order differential equation works for all higher order differential equations.
I'm aware of that, but we are also conscious of the fact that the computation time. Yes. When you bring higher one to first order, your computation drags.
Yeah, you're right. Excellent. You're right. Okay, Dr. Seun, please just quickly help us do that before I close.
That's what I want. That's what I want to do now.
And you have to be correct with this one, because the one you sent to me is not correct too. Please, so that you don't miss this guy.
Okay, is it the email?
Yes, your email, yes. You have to be very, very correct.
I have 3 emails, so I'm trying to check the correct one now.
Please just look for the one that is correct. Otherwise, you just miss this collaboration opportunity. Please, for those of you that are participating, please help us fill the Google form I have put on the. If you're just joining us for the first time, help me to fill the Google form I have put on the chat box. It's very important, please, so that I can send you emails directly. And please follow our LinkedIn page. We have a LinkedIn page. Just try to follow the LinkedIn page. It's also on the chat box. And if you need to contact me directly, you can send an email to this email address on the chat box. I'm going to put that now. If you need to send me an email to this directly. Okay. So Dr. Ogunfeyitimi has sent his his email. So Dr. Mark, you can reach out, please.
I copied it already. Yeah.
Thank you. So please help us fill this Google form, and Dr. Mark, someone says you should also drop your email too, so that we can also. So if possible, you can just put your Google Scholar your Google Scholar or something, so that we can also check what you are doing, and your full name, so that we can check your papers. I think that would be nice too. I maybe I should use the opportunity to say, if you want to understand boundary value method in its simplest form, in its very simplest form, you can check this paper. Because I've done something on boundary value method before, but in the simplest form. You can check this paper. Very, very good paper. And has no much, what they call it, just for beginners. And I think it will help you.
Okay. Please, I need the paper, Dr. Zelos. Please, I need that paper that you want to share with us, please.
I put it on the chat box. It's on the chat box already. Just click that link. Click that link and you get the paper.
Okay, thank you. Thank you.
All right, yeah. Thank you very much, everybody, for joining today. Please always help us share this seminar series to your friends, your colleagues, your research network. And wow. I know this name now, Dr. Mark. You would have used Modebe, not Mark, please. There are some names that we already know. So yes. When you are using, please, anytime you join us, please always use your full name so that we can get to know you very well. And some people we know already. So when you just use some names, and I'm saying Dr. Mark as if, well, that's not your name, it's Modebe, I know. Okay, thank you very much for coming today, and we'll see you next time. I'll send the video and the link to the video and everything that you need for this, for this talk. I'll send it to you.
Thank you, Doctor.
Tomorrow, as soon as I get it. Thank you very much.
Why are you doing?
Bye-bye.
Thank you.
Bye.